The Lewis structure is a visual representation of how the atoms in a molecule or polyatomic ion are sharing valence electrons. In a Lewis structure, each atom is represented by its symbol. All valence electrons must be represented by dots or lines. Each dot represents one valence electron. A line is equivalent to two dots. Lines or dots drawn between symbols of two atoms represents valence electrons shared by the two atoms, meaning bonded pair. For polyatomic ions, the Lewis structure must be enclosed in square brackets with the charge of the ion as a superscript. By following the rules below, the Lewis structure can be written for covalent compounds and polyatomic ions. Count the total number of valence electrons, adjust for charge if an ion, by adding one electron for each negative charge and subtracting one electron for each positive charge. So you got to figure out the valence electrons by looking at the periodic table and counting for each element how many valence electrons there are. Okay, that's accounting for the S and the P blocks. Draw the skeleton of the structure. Typically, the least electronegative atom is in the central. Most obvious one most of the time, except hydrogen is never it. Hydrogen is always on the outside. Complete the octet around each atom surrounding the central atom. Except hydrogen only needs 2 electrons. Beryllium only needs 4, and boron and aluminum typically have 6 electrons for a full octet. Count the number of electrons placed in step 3. Compare the number of electrons placed to that available, meaning subtract place in number 4 from available in number 1. So available minus placed. If they're equal, we verify that the central atom has 8 electrons around it. Watch the exceptions, boron, aluminum, and beryllium. If the central atom has 8 electrons, then you're finished, except you could check for formal charge, which we will discuss later. If the central atom does not have 8 electrons, it indicates that the electrons must be shared differently. There's a deficiency in the electrons needed, and a multiple bond is present. 2 electrons fewer than the octet suggests a double bond. 4 fewer suggests a double bond, 2 double bonds or a triple bond. To attain a multiple bond, move 1 or 2 electron pairs, depending on whether the bond is to be double or triple, from the surrounding atom to the bond connecting the central atom. Typically, multiple bonds are done with carbon, nitrogen, oxygen, and sulfur, but not with hydrogen or the halogens. So, once again, we will compare our numbers of available to place. If we get a positive number, we verify that the central atom has 8 electrons around it, watching the exceptions. If the central atom does not have 8 electrons, then add electrons to the central atom to obtain an octet and account for these in your comparison. If you have an octet around the central atom and there are still electrons left over, place the extra electrons on the central atom. Typically this occurs when d orbitals are available. That's an n equal 3 or higher, which allows for more than an octet, which we call an expanded octet. Typically, carbon has 4 bonds in a Lewis structure, hydrogen has 1 bond in a Lewis structure, and the halogens have 1 bond and 3 lone pairs. Let's look at an example. We'll start off with a simple one first. Let's look at HCl. First, you must count the valence electrons. Well, hydrogen has 1. Chlorine, if you count, will have 7 electrons. It's in a group 7. Therefore, it gives us a total of 8 electrons available. Step 2, draw the skeleton with the least electronegative atom as the central atom. Well, in this case, it's only 2. We're going to call chlorine the central atom and hydrogen that being attached to that central atom. So we have our skeleton. Complete octets around each atom surrounding the central atom. Well, the only atom that's surrounding what we're calling the central atom, chlorine, is hydrogen, so we will complete that with 2 electrons, since that's all it needs. Count the number of electrons placed. 2. Subtract the electrons placed from available. Okay, remember we had 8 available. We placed 2. That gives us a total of 6 electrons still available to place. We have a positive number of electrons of those left over with no octet no octet around the central atom. Notice we only have 2 electrons around the central atom. Therefore, we can add electrons to complete the octet around the central atom and account for those electrons. So it's going to take 2, 4, 6 more electrons to get an octet around chlorine. So I have 8 around chlorine and 2 around hydrogen. If I subtract that, that means I have none left. The final Lewis structure is here, except typically we change the bonded pair to a line instead of leaving it as dots. So here is your final Lewis structure. Let's do H2O. Hydrogen has 1 electron, valence electron. You got 2 atoms, so you're going to multiply by 2, so that gives us a total of 2. Oxygen's in the 6th group, so it has 6 electrons, so we have a total of 8 electrons. We're going to draw the skeleton with the least electronegative atom in the central. Well, since all we're dealing with hydrogens and oxygens, oxygen has to be the central atom. Next, we will complete the octets, or duets in this case, since we're talking about hydrogens. So then we count how many we placed, which is 4. And then we subtract that from our available amount, which means I still have 4 electrons available. So then I'll look at the central atom. Did I complete an octet there? The answer is no. I'll only use 4, so I can use these 4 to put on that central atom to complete its octets. When I do that, now I can see that oxygen has 8. Hydrogen has 2 on each of them. Therefore, that's my Lewis structure. Only one thing left is I'm going to change the bonded pairs to lines. NH3. Hydrogen is 1 electron, times 3 is 3. Nitrogen in group 5, so I have 5, so that's a total of 8 electrons. Gotta draw my skeleton with the least electronegative atom, and hydrogen can't be it, so that obviously means it's going to be nitrogen. I want to go ahead and complete my duets around my hydrogens. So I add 2 around each one. Add that up. There's 6 placed. I got to compare that to my available. 8 and 2 means I'm going to have 2 more electrons available to complete my octet around my nitrogen. So I'll put my 2 on that. Now I'll look. I have 8 around nitrogen, 2 around each one of the hydrogens. So therefore, that's my Lewis structure, with the exception that I'm now going to take those bonded pairs and put lines. Caution here, a Lewis structure is a 2-dimensional representation of a molecule or ion. Its intent is to show how the valence electrons of atoms are distributed in the molecule. A Lewis structure does not necessarily depict the actual shape of a molecule or ion. However, we can use it to deduce the actual shape, which we'll be covering in another section, which will be the next section. For example, the previous Lewis structure we have drawn water and ammonia. They do not reflect the actual shape of the molecule. The 2D drawing of water gives the appearance that water is linear, meaning the atoms, the hydrogen, are 180 degrees between them. While in reality, the shape is angular or bent. The hydrogens are about 109.5 degrees between them. So here's your 2D Lewis structure. And you can see we got it in a line that makes it look like it's 180 degrees between these hydrogens, but that's not true. In reality, hydrogens are kind of bent, and you also have these 2 lone pairs. It's really in a tetrahedral arrangement with all 4 of these groups, which is a molecular arrangement of bent. The hydrogen atoms are basically bent. Now, in a 3D drawing, which this is, when you have a solid line, that's where we're saying it's in the plane of the paper. If you draw dotted lines, we're saying that indicates that it's going into the plane of the paper. If you have a wedge, that means it's coming out at you, out of the paper. So the way this is drawn, we're saying this lone pair is in the plane of the paper. These 2 hydrogens are going into the board or into the paper or the PowerPoint presentation, and this other one is coming out. So these hydrogens are not in a straight line. They are bent and 109.5 degrees apart. In the ammonia, the actual 3D shape is trigonal pyramidal. we drew it as this method for the 2D Lewis structure, and it looks like it's going across in 2 hydrogens and 1's below, but that's not really what's happening. What we have is a trigonal pyramidal shape where you have these 3 hydrogens basically forming a pyramid at a base of a pyramid. So it's important to be able to draw a Lewis structure because you're going to have to draw this before you can figure out the actual 3D molecular shape. And we're going to talk about how to go from your 2D shape to your 3D shape in the next section. Let's do boron trifluoride. Count the valence electrons. Well, fluorine's in group 7, so it has 7 electrons, so times 3, that's 21, and boron's has 3 electrons. That's a total of 24 electrons. Draw your skeleton with the least electronegative atom. Okay, that would be boron in this case. We need to next complete our octets around the surrounding central atom, so that's the 3 fluorines. We do our octets around those. So I threw 8 electrons around each one of these. Count your number of electrons placed, which in this case is 24. Subtract, that means I have none left over. Well, I have no electrons remaining, and there's not an octet around that central atom, but recall, boron was one of those exceptions where 6 electrons is a complete octet. So finally, what we're going to do is just take those bonded pairs and put our bonds. So here's my completed Lewis structure for boron trifluoride. Arsenic pentafluoride. Count our valence electrons. Fluoride has 7 times 5, 35. Arsenic 5. Which means I have a total of 40 electrons available. Draw our least electronegative atom in the center, which would be arsenic in this case. Next, we complete our octets around it. So I'm going to put 8 electrons around each one of these fluorines. Count the number of electrons placed, which would be a total of 40. You got 8 around 5 fluorines. That's 40 placed. Now I got to subtract that 40 from available, which is 40 minus 40, which means 0. I have no electrons remaining. But now I got to count my electrons around the central atom, and I should have 8. Let's see. 2, 4, 6, 8, net 10. I got 10. Okay, how can I have 10? It's supposed to be 8. Well, typically this occurs when d orbitals are available. If we're at n equal 3 or higher, which allows for more than an octet around the central atom, we can have an expanded octet. This meets that condition, so arsenic can have more than 8, and that's why it has 10. Finally, change the bonded pairs to lines, and the structure is complete. Count our valence electrons. I got 2 chlorines at 7, that's 14. Oxygens in group 6, that's 6. Carbons group 4, that's 4. That's a total of 24 electrons. Draw my least electronegative atom in the center, which would be carbon. Put my other 3 around it. Complete octets. I'm going to put 8 around each one of these chlorines and around this oxygen. Count the number of electrons I have. 2, 4, 6, 8 times 3. That's going to be 24 electrons have been placed. I now have to subtract my place from my total, which gets me 0. Next step, we'll look at the central atom and see if I have an octet. I have no electrons remaining, so I can't add them to the central atom. But notice I only have 6 electrons around the central atom. That's not an octet, and it's not an exception. This indicates a deficiency of electrons, and a multiple bond is present. There's not enough electrons to complete the octet for all the atoms. Therefore, I must share some additional electrons between atoms. Well, typically you don't do that with the halogens, so the only choice is the oxygen. So to attain a multiple bond, we must move one pair of electrons from the surrounding oxygen to the bond connecting the carbon and oxygen atoms. Note this is not typically done with the halogens. So I'll take 2 electrons and move them between the 2. And now what you see is I have 8 around my chlorine, 8 around my chlorine. I have 2, 4, 6, 8 around my carbon. and I have 2, 4, 6, 8 around oxygen. So everything has an octet, and I still only used my 24 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So finally, all we got to do is take our bonded pairs and make them into, draw lines, which gets us the following. I got a single bond between carbon and chlorine for each of them, and a double bond between carbon and my oxygen. Let's look at CH4O. 4 atoms of hydrogen times 1 is 4, oxygen 6, carbon 4, total of 14 electrons. Remember, I'm getting these numbers from the valence electrons that are on the periodic table, the S and the P blocks. Or you could just look at their group numbers and it tells you the valence electrons. Okay, you draw your skeleton with the least electronegative atom in the central, which in this case will be carbon. Complete octets around each atom, which will be 2 for each of the hydrogens. Also notice I had to do a little deciding on how to put my species together in this case. I know that hydrogen can only attach in one spot, so that meant that my carbon and oxygen had to be attached, and then my hydrogen went to the outside of the oxygen. So I complete my duets and octets. Count the number I placed, which is 14. So I subtracted, that means I had none left. So hopefully I have an octet around my central atom. If not, then I have to do some adjustment. But if we look at it, I got 2, 4, 6, 8 around carbon, 2 around each of the hydrogens, and 2, 4, 6, 8 around oxygen. So I don't need any double bonds or anything. So I can just do single bonds. So there's no electrons remaining, and there are 8 around the central atom. Therefore, this is a complete structure. So finally, I just changed my bonded pairs. NO3 minus. Count your valence electrons. 3 times 6 is 18, and 5 for nitrogen. That gives me 23 electrons. But notice that I have a charge on this, so I got to account for that. That means I have an additional electron. So I need to account for the charge on the ion. The -1 charge means there's an additional electron available that we must add. So I add my 1. So really I have 24 electrons available. Draw my skeleton. I'm going to put nitrogen at my central atom, and note that since this is an ion, I must also have brackets in the charge. So I have my skeleton and my brackets and a charge on it. Complete the octets. So for around each one of these oxygens, I will put 8 electrons. Next, I will count the number placed, which was 24. Subtract my 24 from what I got available, which means none. So now I got to check, since I have no electrons available, do I have an octet around that central nitrogen? And got 2, 4, 6. The answer is no. That means I have a deficiency in electrons, which means I'm going to have to do some double bonds. So I have no electrons remaining, but notice there are only 6 around the central atom. It's not an octet. It's not an exception. This indicates a deficiency of electrons and a multiple bond is present. There's not enough electrons to complete octets for all atoms. Therefore, we must share some additional electrons between atoms. To attain a multiple bond, we must move 1 pair from a surrounding oxygen atom to the bond connecting the nitrogen and oxygen. So we take 1 pair and move it and make a double bond. Notice when we do that, we still have 8 around this oxygen. We still have 8 around this oxygen. This oxygen still has 8, 2, 4, 6, 8. And now nitrogen has 8, 2, 4, 6, 8. Finally, we take our bonded pairs and put lines. So we have a single bond between 2 oxygens and a double bond between the other. And for this to be a complete Lewis dot structure, you have to have the brackets as well as the minus charge. Now, which oxygen gets the double bond in the nitrate ion? Notice there was 3 oxygens. Now, which one would I do it with? Does it matter? It is possible to have more than one way of distributing valence electrons for a given molecule or ion. Each of these unique ways is called a resonance structure. The conductivity in resonance structures is the same. Resonance structures represent the same molecule. The existence of two or more resonant structures generally indicates that none of the structures adequately represents reality. Reality is probably a hybrid of the resonant structures. In the nitrate ion experiments, it shows the bond lengths to be similar and are a combination of a single and a double bond for all bonds. The bonds are shorter than a single bond, but longer than a double bond. Basically, there is a delocalized bonding in which a bonding pair of electrons is spread over a number of atoms and not localized just between two atoms. So basically, this additional pair of electrons is shared between all three oxygens, not just between one oxygen and one nitrogen. When we draw the resonant structures, we draw all the structures with double-headed arrows between them to indicate the resonance. So we have to draw all three structures. So for the nitrate ion, a complete Lewis dot structure would look as follows, where you draw your Lewis dot structure as we did earlier. Then you draw a double arrow, headed arrow. Then you draw it again, but you put the double bond in a different location. And then the double arrow and draw the last one where the double bond is in a different location. You have to draw all the possible structures. Now a shortcut to doing this, short notations, you may sometime run into something written as such, where it has a structure drawn once, but then it has a single line for all three spots and a dotted line in all three spots. This is giving an indication that it's a single bond or a double bond in the three locations. Let's look at a cation. You got hydrogen, 4 of them times 1 electron. You got 5 electrons. That's a total of 9. But since this is a positive, that means I've got 1 less electron. So I need to account for that. So then I'll take that plus 1 and I will subtract 1 electron from that charge, giving me a total of 8 electrons available. Draw my skeleton, which means I got to put nitrogen in my central atom and also use my brackets in my charge since this is an ion. Next, we complete the octets, or in this case, it'd be duets, since they're all hydrogens. So I put 2 electrons around each one of my hydrogens. See how many I placed. I placed 8. I have 8 available. Subtracted, that gives me 0. So hopefully I have 8 electrons around my central atom. Otherwise, I have to do some multiple bonds for deficiencies, or if I have any additional electrons, then I'll put it on the central atom. In this case, we have 0. So I'll look at it. I got 2, 4, 6, 8 around nitrogen. So this looks like a legitimate Lewis dot structure. So the only other issue we have is to change our dots into lines. So my final Lewis dot structure looks as such. Remembering I got to do my Lewis dot structure with the brackets in the charge. Xenon tetrafluoride. Got 28 electrons from the fluorine. 8 from the xenon gives me a total of 36. Draw my skeleton. In this case will be xenon. Next will be complete your octet. So I will put 8 around each one of these fluorines. That means I placed 32 electrons. 8 times 4. Now I'll compare that to my available, which is 36. That tells me I got 4 electrons available. If I look at my central atom, I have 2, 4, 6, 8. I have 8 around there, but I still got 4 more available. Well, this is another one of those examples where I have d orbitals available, so I can expand this octet. So I have a positive number of electrons, but there are already 8 around it. Since xenon has d orbitals available and 3 or higher, it can accommodate more than an octet around it, expanded octet. Therefore, we'll just add the extra electrons around the central atom. So xenon ends up being a total of 2, 4, 6, 8, 10, 12 electrons around the central atom. So now all you do now is take those dots and change them into bonded pairs. And our Lewis dot structure looks such. You have your 4 fluorines around it, bonded pairs between the fluorines and xenon, and then 2 lone pairs on the xenon. This becomes important when we start doing the molecular geometry. This will have a different shape, as we discuss in the next chapter. HCN, hydrogen 1, nitrogen 5, carbon 4, that's a total of 10. Central atom, least electronegative in the center, which would be carbon. Complete our octets would be 2 around hydrogen and 8 around nitrogen. Count how many you placed. You placed 10. Compare that to available. You have none left. So then you check your central atom and you see I only have 4 electrons around it. So that means I'm going to have to do some double bonds or triple bonds because I have a deficiency in electrons. So this indicates a deficiency of electrons and a multiple bond is present. Not enough electrons to complete octets for all atoms. Therefore, must share some additional electrons. So what we'll do is take 2 off that nitrogen and move it between carbon and nitrogen. After I did that, we still used the 10 electrons. However, I got 2, 4, 6 around carbon. I still have 8 around nitrogen, so I'm going to have to do this again. This only increased the number of electrons around it to 6, therefore we must do it again. Now I got 2, 4, 6, 8 around nitrogen and 2, 4, 6, 8 around carbon. We only used the 10 electrons. This is my Lewis structure, except now I will take those bonded pairs and put lines. So I have a single bond between hydrogen and carbon and a triple bond between carbon and nitrogen. Homework 66.